to talk about neutrinos most of the time, and finally I will talk about the INO, India-based Neutrino Observatory. But that part is very important, of course. How many of you are engineering students, and how many? All are engineering. Oh, yesterday it was all science students. So you are doing first year of your engineering? Yes, first year or second year? First year. First year. Okay, good. Good. Very important discoveries have been made in the past 20 years in neutrino physics and neutrino astronomy. Although the results of this project will be ultimately physics and astronomy, but the project itself is a major engineering project. So I want all of you to take interest in it. And I will stress that point towards the end when I come to the detector. Neutrinos are elementary particles which fill the universe in great abundance, but are very elusive. They hardly interact. Trillions of neutrinos, trillion means 10 power 12. That many neutrinos are passing through our bodies every second without affecting us. Our sun alone is producing plenty of neutrinos through the thermonuclear fusion reactions, which are giving us heat and light and keeping us alive. So you see the connection of life with neutrinos. 70 billion neutrinos per centimeter squared per second are falling on the earth. This I will be able to calculate. You will see that it is a very easy calculation for you to do. 70 billion. One of the most important developments of the last decade, last 2 decades I must say, is the direct experimental proof that the sun's heat and light are produced by the thermonuclear fusion reactions in the sun. The second important discovery is that neutrinos have mass, although it's a very, very tiny mass. Until this discovery, it was thought that neutrinos are massless particles like photons, the quanta of light. This discovery is expected to have a profound impact on our knowledge of the universe. Of all the elementary particles of nature, neutrinos are the most elusive. Studying the properties of neutrinos is a crucial step in mankind's inward-bound path of discovery, unraveling the mysteries of matter and the forces that hold it together. The resulting understanding will explain not only what we see around us today, but also can be taken back in time and applied to the very early universe. How did the universe begin? How did it evolve into its present form? This is the basic importance of, one of the basic importances of neutrino research. I'm giving you an example here. The universe is supposed to have started as a Big Bang in which equal amount of matter and antimatter, equal numbers of particles and antiparticles presumably were produced. But now we see only particles around, only matter. Antiparticles are produced in the laboratory artificially and then studied. So what happened to all the antiparticles? Antiproton, anti-electron and so on. How did they disappear? That is one of the basic questions. If neutrinos are Majorana particles, unfortunately I will not be able to explain it, but if there is question at that time I may be able to explain. If neutrinos are Majorana particles, then this can be explained. That is the fundamental importance of neutrino research. Actually, to see whether, to determine whether neutrino is a Majorana particle is still not done, and that experiment also will be mounted inside the INO cavern. In my opinion, that is the most important question to be settled about neutrinos. These developments have led to very active planning of many more neutrino laboratories all over the world. For a considerable part of the neutrino physics is yet to be discovered. What has been discovered is only the tip of an iceberg. So a grand competition is on between different countries, United States of America, Canada, Europe, Japan, Korea, and China. What about India? Actually, India was a pioneer in neutrino physics. The very first detection of cosmic ray produced neutrinos was made in the Kolar Goldfield experiment in 1965. Professor Mondal has come. He will be, he is one of the pioneers in the experiments in Kolar Goldfield, not in the original 1965, but the subsequent experiments. But the KGF laboratory was closed in the 90s because of the closure of the KGF mines. This was unfortunate. They closed it because there was hardly any gold in that. But this was unfortunate because fundamental truth, fundamental science, in my opinion, is more important than gold. But anyway, we lost it. There is no point in crying over spilt milk. It is the study of these cosmic ray produced neutrinos that led the Japanese physicists to win the Nobel Prize in 2002 and again in 2015. So clearly we missed the boat. Can we recover the lost initiative? We can and we must. The India-based Neutrino Observatory INO project has been conceived with this objective in view. So this is the brief outline of my talk. Introduction I have already given. Summary of our present knowledge of fundamental physics, which will be a background, because neutrino physics is a part of particle physics, fundamental particle physics. And then I will go to a brief history of neutrino physics, because I feel that the best way of understanding physics and even chemistry and biology is through history, how particular things were discovered. And so that will be very important. Then I go to the main part of the talk, namely neutrinos from the sun, called solar neutrinos, atmospheric neutrinos, which are actually neutrinos produced from cosmic rays. And then from that, I will derive the concept of neutrino oscillation, and from that, the neutrino mass, how the discovery of the neutrino mass was made. Finally, of course, I come to the important topic of INO. So first, I give a capsule presentation of our current knowledge of fundamental physics. 100 years of fundamental physics, starting with the discoveries such as radioactivity, electron, neutron, and positron, which, of course, you might have studied in the school, and revolutionized by relativity and quantum theory, have culminated in the summary I am giving now. According to this knowledge, the universe consists of two components, particles and fields, roughly. The particles I have given on the left and the fields I have given on the right. Now we know that the proton and neutron, the constituents of the nuclei, are made up of further fundamental particles called quarks. Both proton and neutron are made up of 3 quarks each, the U and D quarks, sorry. The U and D quarks. Once you have made the nucleon and then the nuclei, then you can put the electrons around. That makes the atoms, molecules, and all the things which we see. So you see, all the things which we see are configurations of different numbers of this U, D, and E only. Just imagine this whole complicated universe, as far as we can see, is made up of only 3 fundamental constituents. Then if you add the neutrino, which plays an essential role even in the thermonuclear fusion reactions, which I am going to describe, and so life will come from that. So just with this quartet of particles, one doublet, which is called the leptonic doublet, and then the quark doublet, a quartet. With this quartet, a whole universe can be made. But nature, for some very important reason, has decided to repeat this quartet twice more. There are heavier quarks and there are heavier electrons. E is the usual electron of which all of us are made. Then mu is a heavy electron. Tau is even heavier. Then along with each of these charged particles, there is a neutral particle which we call neutrino. So there are 3 kinds of neutrinos, nu E, nu mu, nu tau. That is what you have to remember for the talk. This I think I will ignore for the time being. So history. Neutrinos were born in the mind of Pauli. All of you might have studied about Pauli exclusion principle, which is very important in atomic structure. And the same Pauli solved a very important problem in physics. When radioactivity started and alpha, beta, gamma rays were identified by Rutherford and others, when they studied the beta rays are nothing but electrons coming from nuclei when the nuclei decay. And there was a strange thing. Instead of coming with unique energy like alpha particle, the energy of the particle which comes out has to be the difference between the initial energy and the final energy. But neutrinos came out with a continuous energy spectrum. This was a big puzzle. People like Niels Bohr thought that maybe energy is not conserved in fundamental process. But Pauli had a different idea. He said another particle which is unseen, an invisible particle, was emitted along with the electron. That was Pauli's suggestion. But I do not know that how seriously Pauli took his own suggestion. He did not even publish it as a scientific paper. He just sent a brief letter giving this idea to some conference. And the person who took the idea seriously was Enrico Fermi. He constructed a complete theory of what we call beta decay, weak interaction, in the year 1932 or 33, based on Pauli's idea, using the fact that the electron and neutrino, electron as well as the neutrino are simultaneously created. This creation was so far not considered in physics. That is achievable only in a theory called quantum field theory. Fermi mastered that, and constructed that theory. And that theory proved to be the correct theory for beta decay until very recently, until the recent developments improved it on what we now call the standard model. And this Fermi's theory was subjected to experimental tests by studying the beta decay from various nuclei through the in the subsequent years, and all of them verified Fermi's theory is correct, and hence verified neutrino existed. But there were two experimentalists, Kovan and Reines, who said that is not enough. If a theory is to be a theory has to be always checked by experiment. If neutrinos are there, I have to detect them. So they decided to go near nuclear bombs. Remember, this was 50s when nuclear bomb tests were going on all over the world, and they wanted to go near one of those sites and detect the neutrinos, because every fission bomb produces many fission fragments. All of them are radioactive, in particular beta active, and hence in every beta decay a neutrino is emitted. A copious number of neutrinos will come, but of course they were prevented from doing so because it is a dangerous thing. But nuclear fission reactors also produce the same thing. Every fission process produces. So every fission reactor is a copious source for neutrinos, actually anti-neutrinos. So they managed to go near the reactor, nuclear reactor in US called Savannah River reactor, and managed to detect the anti-neutrinos coming from them. There again a story is there. When they wanted to have financial support for their project, apparently Pauli wrote to the authorities saying that don't give money because my particle can never be detected. But they got the money and they went ahead and detected it. That is itself is a very interesting experiment. You have to say it, say briefly at least, because that is the first neutrino experiment done on the Earth. They had a huge detector in which some hydrogenous material like paraffin was there, and the neutrinos, I'm sorry, the antineutrinos come and get captured by the proton in the paraffin, and so antineutrino plus proton gives rise to neutron plus positron. They managed to detect both of them. Positron, I don't know how many of you know, positron is the anti-electron. It annihilates with an electron in a material and gives two gammas, two photons with a well-defined energy, 0.51 energy. They detected that, and neutron gets absorbed by some absorbing material like cadmium and emits photons. That also they detected. Although it was a very difficult experiment, nobody would believe that it could be done. And these people had two signals, two correlated signals, time correlated signals, and that is why it was very believable. So that happened in 1954. So now I will shift and go to atmospheric neutrino experiment done in the Kolar goldfields. I have already said it. Homi Bhabha, when he started cosmic ray research in this country, he was a cosmic ray physicist, theoretical work, lot of work he had done. He wanted to verify many of his predictions by experiments which can be done. He sent one group to Kashmir. In Gulmarg, they had set up a cosmic ray laboratory which existed until recently. In fact, I have even visited it. Now I think it does not exist. He sent another group to study the cosmic ray intensity as a function of the depth in the Earth. Now that group started detecting the cosmic ray particles in the Earth as a function of the depth. Mostly it is muons. It is muons, the heavy electron which has high penetrative power, and that is what survives when you go down in the Earth. And they measured the number of muons which come from cosmic rays as a function of the depth. I think they went down to perhaps up to roughly 2 kilometers. At one depth, pardon? Later.
Only 1,000 feet.
1,000 feet.
Up to 1,000 feet.
Okay. So even at that, at one depth, they found that the detectors fell silent. It did not detect any muons. The detectors were working. They checked that. Still it did not detect. So they realized that almost all the muons have been filtered by the overlying rock, so that now the neutrinos are hardly interacting. And so if there are well interacting particles like muons around, you will not be able to see the neutrino. It is like going out, if you go out, you will not see stars. Stars are there because the weak light from the star is wiped out because of the abundant light from the sun. But when the earth comes and prevents the sunlight coming, we see the stars. It's exactly like that. So we have to have at least 1 kilometer of rock all around the detector to see the neutrinos. So the experimenters went ahead, waited for a longer time, and managed to detect the neutrinos in 1965. That was the first atmospheric neutrino detection which happened in India. Now I will shift track and go to the solar neutrino experiments. Again, the same story. I will talk about the Bethes theory. It was already known that these thermonuclear fusion reactions are the ones which produce heat and light, and hence they are producing neutrinos. But again, Davis, an experimenter, he was actually a chemist, he said that is not enough. Actually, Nobel Prize was already given to Bethe even before this time, even though the neutrinos are the only convincing experimental proof of Bethes theory. Even before the neutrinos were detected, Nobel Prize had been given to Bethe because he had other contributions also, but the main contribution was this solution of the solar neutrino, the thermonuclear fusion. But anyway, Davis decided to do the experiment. He started it, I think, in 1970. The experiment went on for 2 or 3 decades, and because of the extensive series of experiments he did, finally he managed to get a number for the number of solar neutrinos detected by him. That number was smaller than the number which you can calculate. How many neutrinos should come from the sun, you can calculate. That is the theoretical number. And that number, the experimental number, was roughly 1/3 of the theoretical calculated number. This became known as the solar neutrino puzzle and stayed for a long time. People at that time suggested a solution for this, but many people did not believe that solution. That solution is oscillation, I am going to talk about. They did not believe it because the number of neutrinos coming from the sun, although you may calculate, your calculation may be wrong. You may be using a wrong model of the sun. So that is the reason why this was not a believable discovery of the neutrino oscillations. That is reserved for the atmospheric neutrino experiment. The atmospheric neutrinos, which was originally detected in India, was taken up for detailed study by the Japanese. So it is they who showed, because their experimental research did not depend so much on theory. I will talk about it a little later. And so they were the people who are supposed to have first discovered neutrino oscillations, and hence through that the neutrino mass. So that is the brief history. But if you go to solar neutrino problem, that also got solved by a very elegant experiment done in Canada, the Sudbury Neutrino Observatory in 2002. I will talk about that. So both solar neutrino problem and atmospheric neutrino problem were solved by using the hypothesis of neutrino oscillations. And neutrino oscillations means neutrino has mass. I will tell you, I hope I will have time for that. Then one more experimental discovery I should mention. 2005, an important discovery was made again by another Japanese detector, Comland. They detected what are called geoneutrinos. What are geoneutrinos? Geoneutrinos are neutrinos from radioactive ore like uranium, thorium, radioactive potassium, buried deep in the earth, mantle, core, wherever they are. And from the direction in which the neutrinos were coming, you can see where the neutrinos are buried. So this gives the first chemical input in our understanding of the earth. That is the importance of this. So an important geophysical or geochemical window was opened by neutrino physics. Finally, hopefully, new discovery will be made by INO in future. So again, solar neutrinos. Again, let me start with history. In the 19th century, around 1850 or so, this was a burning problem. How does sun produce energy? And two famous physicists, Helmholtz and Klein, tried to solve the problem. They had this idea that every star, including the sun, starts out as a gigantic cloud of hydrogen. And since the mass of that cloud is so high, because of gravitational attraction, all of them turn to go to the center. There is an infall of the hydrogen gas towards the center. And so the speed goes up. When the speed goes up, the temperature goes up, and that is what sun is. That is That was their theory. But since they were very good physicists, they could also calculate how long this process will keep the sun alive. They found it was of the order of 1,000,000 years, at the most 10 million years. But by that time, enough about the Earth's history was known. Geologists knew about it. And Earth had lived for 1,000,000,000 years, not million, 1,000,000,000 years. So how can Earth have a lifetime of 1,000,000,000 years when the sun has a lifetime of only million or 10 million years? This was a big problem, and people went on arguing about it. Meanwhile, Charles Darwin also joined the quarrel because his theory of evolution also needed 1,000,000,000 years. So they went on fighting with each other, abusing each other, saying that you do not know enough physics and so on. But the problem was solved only after new things were discovered in physics. That was the discovery of nucleus by Rutherford in 1911. And once the enormous amount of energy locked up inside the nucleus was discovered, Eddington, the famous astronomer, solved the problem by saying it is the thermonuclear fusion reactions which produce the sun's heat and light. Eddington said that, but again nuclear physics had to advance to a level where when the problem could be completely solved by the master nuclear physicist Hans Bethe in 1939. Although earlier, 1 year earlier, Weizsäcker had given a partial solution. Bethe's paper is a masterpiece. Anybody interested in neutrinos should read that paper. It contains everything about solar neutrinos. But Bethe, if you look at Bethe's paper, the reactions, the thermonuclear fusion reactions which he writes are all wrong. They don't have neutrino in it. So it's they are all unbalanced equations. I'm sure Bethe knew it because Bethe used the Fermi's theory, and Fermi's theory involves emission of neutrinos. I think he omitted it because he thought that his paper will not be published if neutrino is mentioned, because neutrino had not become popular. I mean, a journal like Physical Review would not accept it, I think. He thought perhaps. Anyway, whatever it is, this was a big setback for neutrino physics. This is a big setback for neutrino physics, in my opinion, because the authority of Bethe was so strong that in the subsequent 2 decades, no astronomy book or astrophysics book mentions neutrinos. This is very unfortunate because if neutrinos, the importance of neutrinos had been known earlier, neutrino physics would have picked up much earlier. Because neutrinos, observation of neutrinos from the sun is the only experimental evidence for the thermonuclear hypothesis. Otherwise, it is only a hypothesis. Second important point about neutrinos, solar neutrinos, is neutrinos provide with a sensitive thermometer to measure the temperature deep inside the core of the sun. Because these thermonuclear fusion reactions happen in the core of the sun, and from that light as well as neutrinos come out, but that light never comes out because it gets absorbed and scattered and so on. Whereas neutrinos, since they are elusive, they don't hardly interact, they come out direct. In 8 minutes, they reach us. The photons which we see from the sun, the light which we see from the sun are emitted only at the surface. So the temperature of the sun outside is 6,000 centigrade. That is the temperature of the outside. And deep inside situation is very different. So I have been talking about the thermonuclear fusion reactions. What is that? That is this reaction. 4 protons, 4 nuclei of hydrogen atoms combine to form 1 nucleus of the helium-4 and 2 positrons, E plus I said, 2 positrons and 2 neutrinos and 26.7 MeV energy. That's all. So you see, it's very easy to calculate the number of neutrinos emitted by the sun. If you go out in the sun and if 26.7 MeV energy falls on your head, 2 neutrinos also should have fallen on your head. So that is the calculation I have done here. The so-called solar luminosity in ergs per second I have given here and convert it into MeV through this formula and multiply by 2 because for 26.7 MeV, 2 neutrinos are emitted. That is the simple calculation I have done. I have put in the solar luminosity, which is well known, and that is the total number of neutrinos emitted by the sun per second. To calculate the flux, divide by 4 pi r squared, where r is the Earth-Sun distance. So any of you can do the calculation. It is given here. You please take it down, or you try to do it. Take the solar luminosity from any tables, any physics book or anything, and this distance you have to, these are the only two inputs which you need. The other input I have already given. You will get that 70 billion, 7 into 10 power 10 per centimeter square per second. These many neutrinos just from the sun alone are passing through our body every second. Night and day, where night, sun is on the other side, the neutrinos simply pass through the earth. As far as the neutrino is concerned, earth is not a barrier. Although this is the basic reaction, it does not go this way, because the probability of 4 protons to join together, even in the very dense solar core, is very small. Because proton has tiny size, 10 power minus 13 centimeter. To meet 4 protons within a 10 power minus 13 centimeter, the probability is very, very, very small. So it does not happen that way. What happens is a series of reactions which ultimately amount to this. One is called the carbon cycle. Some of you might have studied it in the +2 school itself, the carbon cycle. There what happens is a carbon nucleus picks up a proton, becomes another nucleus, that becomes again picks up proton. Like that 4 protons are picked up subsequently, and in the process lot of heat as well as neutrinos are emitted. But if you add and subtract the things from the right and left hand side of the series of reactions in the, finally of course it ends up as carbon. So carbon survives. Carbon is only a catalyst in the process. So, so the basic process is still the same, but it is achieved through a series of reactions. But in the sun, it is not this cycle which is important, because that requires carbon. Sun has very little carbon. With the older stars, which have already manufactured carbon through thermonuclear fusion reactions, in which that will go. In the sun, what happens is the so-called proton-proton chain, in which a proton itself captures another proton, becomes a deuteron, okay, and neutrinos, and the deuteron absorbs another proton, becomes triton and neutrino, like that. Again, a series, it's a much more complicated series of reactions. Again, the sum total of that is the same reaction which I mentioned in the rectangle in the earlier transparency. So it's, I said, actually that calculation which I made is a very simple calculation. Any of you can easily understand the total number of neutrinos. But the total number of neutrinos alone is not enough to do neutrino physics. Experimental detectors always have an energy threshold. They can detect neutrinos only above a certain energy. There is always a threshold. So you have to know the actual energy distribution of the 70 billion neutrinos before you can do an experiment. And that is much more complicated. I am not going to tell you here. I will tell you only the results. The results are that the energy distribution, that is called the standard solar model. The theory of the sun is called the standard solar model. And the result is this. The neutrinos have a dominant branch, which is 99.75% of the neutrinos have, unfortunately, very low energy, only up to 0.42 MeV. And that 0.42 MeV, the dominant branch comes mostly from the PP, the first reaction in the PP chain. Then there is a very weak branch, 0.01% only, but that has the highest energy, even going up to 14 MeV. They are called the boronate neutrinos, because it is the neutrinos emitted in the boron, by the boron nucleus in this PP chain. So it's called boronate neutrinos. This is a high energy branch, this is a low energy branch. So the role of the standard solar model is very, very important if you want to detect solar neutrinos. The standard solar model, again, you start with the gigantic cloud of hydrogen, allow the gravity to take over, this is the whole thing collapses, gravitational collapse takes place, and then at a certain point, the temperature in the core of the sun reaches 15.5 million degrees. Million degrees are needed to ignite the nuclear reactions. So after that, the nuclear reactions take over. So I have given the core temperature there. And the flux of the high energy neutrinos, boronate neutrinos, depends on the core temperature of the sun to the power of 18. So even a small change in the core temperature can change the flux very much. So contrarily, if you detect the flux, even an approximate detection will give you a very good determination of the core. That is why I said the solar neutrinos provide a very good thermometer to measure the temperature of the sun. So let us now go to the experiment. The first experiment I will talk about is the chlorine experiment. That was a pioneering experiment by Davis. I already mentioned it. He had a huge tank of chlorine, which contained some material which contained chlorine, which contained the chlorine 37 isotope, and that absorbed the neutrinos from the sun. Oh, I forgot to mention here. As I already said, actually, gammas come out after a very long time, and so that hardly indicates the nature of the gamma produced here, whereas neutrinos come direct. So the chlorine 37 absorbs the neutrino, this neutrino coming from the sun, and becomes radioactive argon 37. He detects these radioactive argon atoms. And his detection technology was so good. He was a chemist. A lot of chemical operations are there. I think he sends helium gas, which purges out argon also. And then he counts roughly some 10 atoms he is able to count. So look at the level of his low-level counting technology. In fact, the Nobel Committee, he got Nobel Prize. The Nobel Committee, which had a citation in which it said that Davis' detection of these radioactive argon atoms coming from the neutrino reactions is like the following. Suppose somebody picks out 1 grain of sand from Sahara Desert and paints it red and mixes it with the Sahara Desert sand, and asks you to detect, to pick out that particular grain of sand. And he managed to do it in the case of his experiment. It's like that. That is the comparison. Now, chlorine experiment, although Davis claimed he detected them because, as I already said, he detected only 1/3 of them. It is an indirect experiment because argon atom, radioactive argon atoms might have been produced in his experiment by some other method. If somebody says it is not solar neutrino which he detected, nobody can object. This is called a radiochemical experiment, a passive experiment. The tank remains, and he collects the radioactive argon atoms every month or so, and then counts the radioactive atom. That's what he did. A similar experiment can be mounted with gallium. Actually, 2 gallium experiments. They are also passive radioactive elements. So both of them suffer from this thing. They are not direct detection. Now this gallium experiment also detected them, but again at a reduced rate, about half of what you would expect from the theory. Chlorine experiment detected about 1/3. Gallium experiment detected about half. Now the entirely different kind of experiment was mounted by Japanese using pure hydrogen, huge tank of hydrogen, huge. And the solar neutrino ejects an electron from one of the atoms in the water, and that comes forward, and you pick up that direction as well as the energy. And every absorption of neutrino will be recorded. So it's a direct, real-time active experiment. And that convincingly proved that what is being detected are solar neutrinos. They also had a depletion. The reason for mounting gallium experiment is that chlorine experiment, I forgot to mention, the Davis chlorine experiment detects only the very high energy neutrinos. And high energy neutrinos are very difficult to calculate because it's only 0.01% of the total number. The low energy neutrinos are mostly the dominant 10 power 10, 7 into 10 power 10 neutrinos, which I said you can easily calculate, anybody can calculate. But 0.01% of that is very difficult to calculate. There may be even 100% inaccuracy. It may be 0.02. How do you know? So that is the problem. Whereas gallium experiment could detect part of that low energy branch. That was the reason why gallium experiment was mounted. And hydrogen experiment also detects only the high energy part. Okay, let us summarize all this now. So solar core produces the neutrinos. They come and we detect them on the Earth. Here I have defined a ratio. I have written it wrongly. It is the number of neutrinos observed divided by the number of calculated a theoretical number. That number, instead of being 1, was always less than 1, and the actual number is shown here. Davis experiment, the 2 gallium experiments, hydrogen experiments, water experiments. Now, these numbers don't agree among themselves because each of them has a different energy threshold. And so even this difference is important physics information. Okay, so we have to explain this. I will omit the comments on this because I have to hurry up, I think. So what happens? How do we explain this discrepancy? Why is it not 1? So that is where comes the so-called neutrino oscillations. Some of the neutrinos oscillated away into the other varieties, nu, mu, and nu tau. That is neutrino oscillation. What is neutrino oscillation? Nu e from the sun converts, forget about this quantum, this particle W. Nu e gets absorbed by chlorine and becomes argon and electron, and it becomes electron. But if, remember, in one of the transparencies in the beginning when I talked about the fundamental physics, I told you that there are 3 varieties of particles: electron, heavy electron, and heavy tau on there. It's called. Along with that, each neutrino comes, nu e, nu mu, nu tau. Electron has 0.5 MeV. That's the Gordon variety electron of which all of us are made. Heavy electron is 200 times heavier, and this is the 36,000 times, 3,600 times heavier than this. Now, if part of the solar neutrinos got converted into nu mu, this figure has to be changed. Here nu mu, mu minus has to be produced. But mu minus requires 100 MeV. And the largest energy of the solar neutrino is only 14 MeV. It is the energy which gets converted into mass of this particle. Remember, E equal to mc squared. Okay? So, the nu mu cannot be detected. Nu tau also cannot be detected. They escape detection. So, that is the explanation of the solar neutrino puzzle. Why we are detecting only part of the neutrinos? Because they have oscillated away. Okay, at this point, I will give you a story. A famous painter painted cow and grass and showed this blank page. So people asked him, where is the grass? Grass has been eaten away by the cow. But where is the cow? After the grass has been eaten away, why should the cow remain there? That has also gone away. So that is the story which we have. I said that Bethes theory has to be verified by experiment. These great experimenters did verify only part of it. The other part we say that went away by oscillation. But in science, we have to do something better. If part of your neutrinos have oscillated away, those oscillated away neutrinos also have been detected. Fortunately, it is possible. That was done by this elegant experiment in Canada called a 2-in-1 experiment in Sudbury Neutrino Observatory, which gave the results in 2002. Here I have to go a little bit into details of weak interaction. The usual beta decay interaction is called charged current interaction, which involves both a charged particle like electron and a neutral particle like neutrino. There is another kind of weak interaction in which neutrino will remain as neutrino. Neutrino will not become electron or mu. So I hope all of you know that there is a thing called heavy water, which is made up of deuterium, which is made up of deuteron nuclei. Deuteron is made up of 1 neutron and 1 proton. Okay? So take this heavy water, use the heavy water as the detection of the solar neutrinos, and that will have deuteron, and nu e converts one of the neutron in the deuteron into proton. So what comes out is 2 protons and 1 electron. That is called charged current interaction because charged particle is involved. There is another kind of weak interaction which is as important as this, which I discovered only later. It's called neutral current weak interaction, in which neutrino remains as a neutrino. Deuteron goes into its 2 parts, proton and neutron. Now, this nu e coming from the solar neutrinos cannot, nu mu cannot produce mu minus, so that will not happen. But here nu e remains nu e, nu mu remains nu mu, nu tau remains nu tau. So all of them will be detected. So the number of neutrinos detected by this process is the total number of neutrinos independent of oscillation. If that number is larger than this number detected by charged current interaction, you have proved that oscillations existed. That is what the Sudbury Neutrino Observatory proved. The number of neutrinos detected here was roughly 1/3 of the total number of neutrinos. So they proved that oscillations existed. Not only that, by taking the difference, you get the mu plus tau. Not only that, this number tallied with the theoretical number calculated by the solar astrophysicists within the errors. They agreed. So at one go, this experiment proved that the oscillations existed, and the thermonuclear fusion hypothesis of Eddington and the theory of Bethe are correct. So at one go they got both. So what is the lesson of this whole exercise? I've been saying that every theory has to be subjected to severe experimental tests, and in neutrino physics it has been done. And in confronting the theory with experiment, these experimenters have discovered something new, that neutrinos oscillate. So it is not just proving it experimentally, but in that process you discover something new, which you did not expect earlier. Now I shift to cosmic ray. Cosmic rays are nothing but very high energy particles, very high energy protons mostly, coming from outer space, impinging on the earth in all directions. Their energy is much larger. Now we are shifting the energy from MEV to GeV, we go to GeV. Cosmic rays are mostly GeV. So a proton, a very high energy proton, comes and impinges on the upper atmosphere, namely nitrogen or oxygen nucleus, and many particles are produced. And many of them are mesons called pi and k. They decay. You can follow this decay chain. And if you look at the final products, electrons will get absorbed, but neutrinos remain. So that is why the debris of all decays of cosmic ray particles or any other particles coming from outer space is always neutrinos. That is why neutrinos are abundant in the universe. And if you look at this suffix here, you will find that for every E type of neutrino, there will be 2 mu type of neutrino. So the number of mu type of neutrino, nu mu, divided by the number of E type of neutrino, nu E, will be 2. So the theory is as simple as this. This is all one has to verify. So that is what the experimenters try to do. So they put a detector here, and they did look at the neutrinos and their composition. Now nu mu also can be detected because these are high energy, GeV. So it can easily produce the mu minus in the final state. So you have to change your view about detection. Nu mu also will be detected. So they did find that the theoretical number agreed for the neutrinos coming from this direction, for the down neutrinos. But neutrinos can come from all directions because cosmic ray particles are impingent in the atmosphere all over. So, so when they observed the neutrinos coming from this direction, this number continuously changed and became 1 for the neutrinos this way. So again due to oscillations. Because here there are 13,000 kilometers available for the oscillation. So, and what happens is half of the nu mu become nu tau in this process. So finally we have the picture. In the solar neutrino case, nu e oscillates to nu mu, and in the atmospheric neutrino case, nu mu oscillates to nu tau. Neutrino oscillations, I have to say a little bit at least, but I should have some time for INO, I don't know. So I will not spend much time over this, unfortunately. Now, neutrino oscillations is not a very mysterious thing. If you, I don't know how many of you have heard the word quantum mechanics. In quantum mechanics is the correct theory. Our classical theory of Newton and so on are only approximate. In quantum mechanics, a particle also behaves like a wave, especially elementary particles, tiny particles. So neutrino, you have to think of neutrinos a neutrino wave. Then it is very easy to understand oscillation. And instead of thinking about neutrino wave, you can think about well-known light wave. Remember, light wave has a thing called polarization. If you send a light wave in this direction, Z direction, it can be polarized in the X direction or Y direction. These are called plane polarized light. But there is another way of describing the two light polarizations, a circular polarization, either right circular polarization or left circular polarization. And the circular polarization is a linear combination of the other plane polarizations and vice versa. They are superpositions. Although both are equally right and both are equally used, but when you send light through an optical medium, the thing to be used is the circular polarization, because it is circular polarized light which has well-defined refractive index and hence well-defined speed of propagation and so on. So when you send light through an optical medium, at this point, although you may have plane polarization, plane polarized light which you may be sending, you resolve them into its circular components, allow them to propagate. At the end of the journey, the two opposite circular components will have a phase because of the different propagation characteristic, and then you recombine. When you recombine, because of this phase, you will not find, if you send X polarized light, you will not find X polarization alone. The Y polarization also will be there. So the light will be polarized in this direction. That is the rotation of plane polarization by optical medium, which in optics is an important thing. Correspondingly, what is the analogy in neutrino physics? I have talked about this nu E, nu mu, nu tau. They are also called flavor states. They are the analogs of the plane polarized light. And when nu E starts its journey from the sun, it comes out as nu E. But it is a superposition, exactly like I said, these are superpositions of this. There are these well-defined mass states. I call them nu 1, nu 2, nu 3. First of all, instead of 2, there are 3 here. Second, these are the mass states, nu 1, nu 2, nu 3. They are the ones which have well-defined propagation characteristics, because mass is connected to energy. It is energy which decides how it propagates. So we have to resolve this nu E into its superposed components nu 1, nu 2, nu 3, allow them to propagate through space, and at the detector, Davis detector, for instance, you have to again recombine them. When you recombine them, a pure nu E would have partly oscillated away into nu mu, nu 2. So that is all oscillation is. The oscillation probability can be calculated. It depends on two things. One, a certain, it's called mixing angle, which tells you how these states are mixed in order to give this. Then more importantly, an oscillatory factor, sine squared of delta m squared, and the length of propagation and energy of the neutrino. And since now oscillation exists, has been proved by Davis and in the atmospheric physics by the Japanese, so we know that theta is not 0. More importantly, we know that delta m squared is the mass squared difference between these 3 different states. We know that delta m squared, namely m1 squared minus m2 squared. We know that m1 squared minus m2 squared is not 0, because if this is 0, this will be 0. That will not explain the solar neutrino puzzle. So delta m squared, non-zero delta m squared has been discovered. Since delta m squared is not 0, mass exists. Without mass, there cannot be a mass difference. The actual story is more complicated because there are 3 neutrino oscillations. There is another important thing called MSW effect, but I don't have time to talk about those things. I should quickly go into INO. So some 10 minutes at least. I started 15 minutes late. Okay, I will try. But it is INO, so give me 10 minutes. Anyway, yeah, there are other talks on INO, so I will only introduce INO. Well, this is, I have to leave this out. This is the final result on masses and the neutrino masses, but I will not talk about this. This double beta decay, I think Vandana Nanal is going to talk about it. She has finished it. She might have talked about it, because that gives you information whether neutrino is a Majorana particle or a Dirac particle. As I said, that is a fundamental importance, but I don't have time to talk about, so let us go to INO. I have written it as 16-year saga, but it's actually a 20-year saga. We started thinking about it even in the year 2000, and plans were made even in 2001, and still it is not seen the light of the day. That is the level of science in this country. I want to mention this. Some people may have very high idea about science in this country. Science is in the bottom. This project has been opposed by some very wise people in Tamil Nadu, saying that it will kill off people, and all kinds of wrong things are being said. And we have been telling them that what you are saying is completely wrong, but they don't listen to us. There is one politician who has been saying in Tamil Nadu that neutrinos are the most dangerous particles in the world. I will not allow them to enter Tamil Nadu. Even before he has finished this sentence, 10 power 12 neutrinos have passed through his body. He does not want to listen. I want to say to young people like you, INO project is not for me or even for Satya or Naba. We would not even exist by the time the project materializes. It is for you people. So it is these people are obstructing your path of progress. You have to go and get over them. Ask them to remove themselves and allow you to progress. I want to convey this message very strongly. 20 years we have not yet started. That is the kind of Indian science we have got. You have seen all the exhibits there. It might give you completely wrong idea about Indian science. So the reality is very different. As long as such people are obstructing it, how can science progress? Okay, a group of more than 100 scientists and engineers spread over 25 scientific research institutions, IITs and universities in India is actively involved in the creation of INO. It is a unique basic science collaboration in the country. It was approved for funding by government long ago. In 2015, the government even sanctioned 1,600 crore rupees. But what is the use? We are not able to make use of it. So what is the project? Now I already said that 1 kilometer of rock is needed to do the Neutrino experiment and to filter away all the other cosmic ray particles. Instead of going into mine, because the Kolar mine is closed, we now go inside a mountain. Such mountains, the right rock quality exists only in Tamil Nadu. We went even and investigated Himalayan rocks, but they are very brittle. Stability is very important. So I have said nature herself has chosen Tamil Nadu for the Neutrino project. I have been saying this to Tamil Nadu politicians, hoping that that will turn their mind, but it does not happen. So many of you might have known about this city of Madurai. From Madurai, you start west, go about 110 kilometers due west, then the Western Ghats rises like a rock in Thane district. So that is one of the one of the hills there. And there you have to dig a tunnel 2 kilometers horizontally and reach a site which, and construct a cavern, dig a cavern out of that dimensions, 120 meter long, 25 meter and 30 meter other dimensions. And in that cavern only this detector of weight 50,000 tons, a gigantic magnetized detector will be mounted. That is the INO detector. And if you, with that as center, if you draw a sphere of radius 1 kilometer, it will all be rock. Actually, it is 1.3 kilometer from the top. So here a picture of the detector is given. It has 140 or 150 steel plates, each thickness 6 centimeter thick, with a 2.5 centimeter gap, in which the RPCs which are here, maybe Naba will explain it to you, and that is the sensitive detector, resistive plate chamber. This unit will be repeated 150 times, and since it is steel, if you if you look at the density of the steel and so on, you will find that 50,000 tons. Now, why do we have iron? There are 3 reasons. First of all, such a huge structure, stability is needed, so iron is chosen. Second, it is the iron nuclei which provide the target for the atmospheric neutrinos. Atmospheric neutrinos and antineutrinos will hit the iron nucleus and produce either mu minus or mu plus, and that mu plus and mu minus are the ones which are detected by the particle detector, RPC. Neutrinos themselves cannot be directly detected. It is the charged particles produced by the neutrinos which are detected, and this mu plus, mu minus, since they have opposite charge, so that is the third reason for having iron. We want to have iron magnetized. Why? In the magnetic field, the oppositely charged mu minus and mu plus will curve in opposite directions, so you will have the flux of the mu minus and mu plus separately. In spite of so many years of atmospheric neutrino study, they have still not measured these two different charges separately. Because mu minus will be produced by neutrinos, mu plus will be produced by antineutrinos. So the separate measurement of the fluxes of neutrinos and antineutrinos will be the achievement of INO. Nobody else has done it. Nobody is even planning to do it. That is a unique feature. Now you can see the LHC detectors right there in the exhibition, and the famous Higgs discovery was made by that. The INO detector, which I just now have described, will be in fact bigger than any of the LHC detectors. They are only 7,000 or 10,000 7,000 tons, whereas this one is 50,000 tons. But I must also say that those detectors which you will see upstairs, the CERN detectors, are much more sophisticated. Many kinds of detectors put in one, whereas INO is only one simple detector. This is RPC, which will be described by Naba. So our students can see a gigantic particle detector in action right here and work with it. That is INO. I think I will forget. This also I will forget. Neutrinos are the most, this I just want to briefly mention. In fact, there was one transparency on this, but I did not have time to explain it. Are the most penetrating radiation known to us. Just as X-rays show you what are the faults in your body, neutrinos will ultimately show where are the fault lines inside. Of course, there is some information on it based on seismic analysis, but this will be more precise. So ultimate prediction of earthquakes are possible, but that is very futuristic. We have to first master neutrino physics and then have neutrino technology for that. Geoneutrinos I have already mentioned. So this is the most important transparency in my opinion. In addition to making major discoveries, INO will benefit generations of students and young scientists and engineers by training them through participation in a major scientific experiment. Student recruitment and training for INO started long ago, and many students have even got PhDs. They are doing PhD work in many laboratories of the world, and INO will attract them back, hopefully. INO project will also involve an INO center, which is already functioning in a rudimentary way in Madurai. Those of you who have a chance to go to Madurai, you can see. In fact, a prototype of INO detector is already there in Madurai INO center. Although the ultimate aim of the project is neutrino physics, it can be easily seen that it is a major engineering project also. Electronics and related engineering and technology will be important parts of the project. Since there are many engineering students, I want to stress this again. The signals from the detector will require handling some 3 million electronic channels. The fabrication of the enormous 30,000 number of sensitive detector elements, RPCs, to accurate specification will be a technological change. What you will see here is 1 foot by 1 foot, by 2 meter by 2 meter, imagine that, with the glass and that 2.5 centimeter gap and so on, with the specific, exact specification, is a technological challenge. It is being done. Satya will tell you, Saint-Gobain near Madras is already producing them, these RPCs. They are being stored in Madurai, I think. I think that is the last transparency. Yeah. INO will be a unique opportunity for young scientists and engineers as well as students of science and engineering. More information on INO website can be obtained from the TFR website. IMSC website is not quite up to date, TFR website. And these are the two references which will contain more information, especially about solar neutrinos. All those reactions which I did not have time to mention will be there in my resonance article or the article by Indumati Murthy and myself in physics education. Thank you all.